not. You have a lot of work to do. All right, so right here, what we want to do, you are given two separate equations, and what we're going to do is we are going to solve for dy dx just like we have before. And fortunately, for some of you, this is not implicit differentiation. You don't have to move anything around because y is isolated on one side. So if I am just right now finding dy dx, basically I'm telling you to take the derivative. So the derivative of y is dy dx. This is 15x to the fourth minus 2. Everyone good? All we did was take the derivative. This is nothing surprising or any change, nothing new. But now if I ask you to solve for dy, what are you going to do? Multiply by dx. Okay, fine. dy is equal to the quantity of 15x to the fourth minus 2 dx. Okay. So we are going to now separate the notation dy dx because dy will represent the approximate change in y. Dx is the approximate change in x. Okay, it's already been somewhat applied when we were using it to represent the slope. In order for me to take the derivative in b, what do I have to use? I have to use the product rule. So, what is f? What is g? Yep. What is f prime? Yep. What is g prime? Yep. Okay, everybody good. So when we're taking the derivative, we have dy dx is equal to f prime times g plus f g prime. Last step is to solve for dy. Multiply by dx. Everybody good? Okay, all this was just practice. Okay, because now we're actually going to apply. So if I told you, which I did, that dx is representing any change in x, and dy would represent any change in y, we want to use a differential to approximate the change in y, okay, when you are given that x is currently sitting at 1, and I'm telling you it's going to change from 1 to 1.01. Okay, they've given us a few pieces of information, and they also give us the function. So first of all, they want us to find dy. This is our unknown. Do they give us x? Yes, it's 1. What does it mean when it says that x changes from 1 to 1.01? What did they give me? They did. They gave us dx, which is the approximate change in x, which is 0.01. Agree? Okay. They gave us our function y is equal to 1 over x squared. Am I going to use the quotient rule here? I mean, you can, but it's going to take me longer, right? What's going to be easier? Yeah, that's right. Y is equal to x to the negative second. This is a friendly form. Okay, I'm not saying that you can't use the quotient rule, but the 1 is going to go away. It's going to become 0, and you're going to get the same answer. It's just going to take you longer to get there. dy dx is equal to negative 2x to the negative third. Agree? I'll rewrite it in just a second. Okay? But I want to solve for dy. So dy is equal to negative 2 over x cubed times dx. Is everybody okay with how I got what I got? Okay. If they want us to approximate the change in y by using dy to represent that, do I have everything I need to plug into the right side? Do we have our x and do we have our dx? We do. Okay, so up here, we've got dy is equal to negative 2 over 1 cubed times 0.01. Okay, so this is what? Negative 2 times 0.01. So the approximate change in y, which is represented by dy, is equal to what? That's right. So what they're saying is that based on this relationship for this function, when x changes by 0.01, y changes by negative 0.02. Questions? Okay, this can also be applied to what would be considered close to related rates problems. Okay, here we are given the information that the side of a square is measured to be 10 feet, but there's a possible error of plus or minus 0.1. What that means is if there, let's say, are these wooden squares that are being stamped out in a factory. Okay, you would think that in a machine, given a program, they're going to be exact, but things happen, right? Okay, and so what they're saying is that the sides could be bigger than 10 feet or sometimes a little bit smaller than 10 feet. So what we have is our side is equal to 10 feet, and the error means that the sides could potentially change by plus or minus 0.1 foot, ft. So what do I use to represent that? The ds, because it's based on the side, ds. The possible change in the side, right? ds is equal to plus or minus 0.1 foot. Bless you. Everybody good with this so far? That's all they gave us. I mean, we could find lots of things, like we could find the area if we needed to, yeah.
Why don't we add that to the 10 foot or subtract it from the 10 foot to have it like the ds?
Because this is the possible change. Because then the other thing too is that it might not even happen. It might be 10. Okay? All right. So what we want to do is use differentials to estimate the error in the calculated area. Meaning, when we're talking about error, what is the possible change in the area if my sides are off? Does everybody understand what I'm saying? Like, if I told you that they're perfect every single time, which would be a lie, but if they were perfect every single time, we would know that the area would be 100 square feet, right? But because there's a possible error in the sides, we need to know that there could be error in the area. It's hard to say. Okay, so in part A, we know that we can find the area of a square by doing what? S squared. If we're saying that error is also a change, what do I have to do to my area formula? We have to take the derivative. How do I represent the derivative of the area? dA, right. So this is, right here, what this represents is the possible change in the area based on the possible change in the sides of the square. Sorry. Okay. Is equal to, what's the derivative of s squared? Yeah. And how come I don't put an adjunct on it? It's because it's ds. And what's ds? 1. So this is 2s. Okay. Do we know what ds is? Yes or no? Yeah. Do we know what s is? Okay, so what am I going to do here? Yeah. Move the ds. So you've got dA is equal to 2s ds. So what this is, in terms of, this is the change in the area, or basically the possible error. So dA is equal to 2 times 10 feet times plus or minus 0.1 foot. Okay, so the possible change in the area is equal to, no. You got this 2 here.
Oh, yeah, you do.
Yeah.
Plus or minus 2.
Plus or minus 2 square feet, because it's the area, right?
Right.
So what they're saying is, if you've got these wonky sides, even though you probably couldn't tell just by looking at it, it is possible that your area is going to be off by plus or minus 2 square feet. Does that make sense? Okay, so it actually, just by 0.1, which is less than a foot, it could change your area significantly, depending on how you look at it. If you don't care, that's fine too, right? Just depends on what you're using the square for. All right, let's take a look at this last question. we want to estimate the percentage error in the side and the area. So this is a two-part question. And what you need for the percentage error, this is also known as relative error. And if you don't know how to calculate that, I'm going to write it right here, because this is kind of important. Relative error for anything is going to be any type of error, or basically it would be like the change in the side or the change in the area, like dA, ds, divided by the total. So I might be talking about the total area or the total circumference or the total length of the side. Does everyone understand what I'm saying? So this is how you would find relative error. How do you find the percentage then? What do you do with this? Yeah, you would multiply by 100, so this would be the percent error. Does this make sense? Because I'll be honest with you, I didn't know this, so I had to look it up. So this is kind of important. Well, I'm not going to lie. Okay, so here we go. So to estimate the percentage error, first of all, we need to find the relative error, and then we'll multiply that by 100. So we're looking for the error in the side first. So this is for the side. So that means we need to take the error, or the possible change, which is ds, and divide it by the total, which in this case, if we're talking about the side, we need the total length of the side, which would be s. This is just a general formula. Well, we know ds, right? And we know s, so let's plug them in. So ds is plus or minus 0.1 foot. S is 10 feet. What's 0.1 divided by 10? Well, 0.01 times 100. What is the percent error in the side? Plus or minus 1%. This is the error for the side in terms of percent. For the area, we're going to follow the same thing. So if we want the total error or change in the area, how do I represent that? With just dA, right? Possible change in the area over, what'd you say?
The area?
Yeah, over the area. Okay, so in this case, we know what dA is. We found it. It's over here, right? So we have plus or minus 2 square feet divided by, do I know what the area is? You can find it. Yeah, it's 100 square feet, right? It's 100 square feet, so these are gone. So what's 2 divided by 100? 0.02 multiplied by 100. I mean, that's kind of repetitive, right? So then this is what? Plus or minus 2%. Okay? Okay. Questions? Are you sure?